Welcome back to ET Audio Tutorial channel. We hope you will have a wonderful learning experience here with us. You can download and listen to these audiobooks at your preferred time. Our videos are designed as audio podcasts to help you keep studying at times where you may not be able to watch video or as you are completing another task to better use your time. You can listen to these tutorials at night, doing another task, while taking a walk, lunchtime, or anytime you like. This is the first chapter of Freshman Emerging Technologies course taught in all the Ethiopian universities. This chapter deals with Chapter 2, Data Science. It is tailored exactly to the fitting of the Ethiopian Ministry of Education curriculum but is also very useful for any related course. I am very happy you have chosen this channel in your study and politely ask that you subscribe, like and share the channel for more amazing tutorials. Now, without further ado, let's begin our course. Chapter 2, Data Science. In the previous chapter, the concept of the role of data for emerging technologies was discussed. In this chapter, you are going to learn more about data science, data versus information, data types and representation, data value chain, and basic concepts of big data. Data science is a multidisciplinary field that uses scientific methods, processes, algorithms, and systems to extract knowledge and insights from structured, semi-structured and unstructured data. Data science is much more than simply analyzing data. It offers a range of roles and requires a range of skills. Let's consider this idea by thinking about some of the data involved in buying a box of cereal from the store or supermarket. Whatever your cereal preference, tough, wheat, or barley, you prepare for the purchase by writing cereal in your notebook. This planned purchase is a piece of data, though it is written by pencil, that you can read. When you get to the store, you use your data as a reminder to grab the item and put it in your cart. At the checkout line, the cashier scans the barcode on your container, and the cash register logs the price. Back in the warehouse, a computer tells the stock manager that it is time to request another order from the distributor because your purchase was one of the last boxes in the store. You also have a coupon for your big box, and the cashier scans that, giving you a predetermined discount. At the end of the week, a report of all the scanned manufacturer coupons gets uploaded to the cereal company so they can issue a reimbursement to the grocery store for all of the coupon discounts they have handed out to customers. Finally, at the end of the month, a store manager looks at a colorful collection of pie charts showing all the different kinds of cereal that were sold and, on the basis of strong sales of cereals, decides to offer more varieties of these on the store's limited shelf space next month. So, the small piece of information that began as a scribble on your notebook ended up in many different places, most notably on the desk of a manager as an aid to decision making. On the trip from your pencil to the manager's desk, the data went through many transformations. In addition to the computers where the data might have stopped by or stayed on for the long term, lots of other pieces of hardware such as the barcode scanner were involved in collecting, manipulating, transmitting, and storing the data. In addition, many different pieces of software were used to organize, aggregate, visualize, and present the data. Finally, many different human systems were involved in working with the data. People decided which systems to buy and install, who should get access to what kinds of data, and what would happen to the data after its immediate purpose was fulfilled. As an academic discipline and profession, data science continues to evolve as one of the most promising and in-demand career paths for skilled professionals. Today, successful data professionals understand that they must advance past the traditional skills of analyzing large amounts of data, data mining, and programming skills. In order to uncover useful intelligence for their organizations, data scientists must master the full spectrum of the data science life cycle and possess a level of flexibility and understanding to maximize returns at each phase of the process. Data scientists need to be curious and result-oriented, with exceptional industry-specific knowledge and communication skills that allow them to explain highly technical results to their non-technical counterparts. They possess a strong quantitative background in statistics and linear algebra as well as programming knowledge with focuses on data warehousing, mining, and modeling to build and analyze algorithms. In this chapter, we will talk about basic definitions of data and information, data types and representation, data value chain and basic concepts of big data. What are data and information? Data can be defined as a representation of facts, concepts, or instructions in a formalized manner, which should be suitable for communication, interpretation, or processing, by human or electronic machines. It can be described as unprocessed facts and figures. It is represented with the help of characters such as alphabets, capital letters A to Z, small letters A to Z, digits, 0 to 9, or special characters, plus, minus, slash, asterisk, greater, less than, equal sign, etc. Whereas A information is the process data on which decisions and actions are based. It is data that has been processed into a form that is meaningful to the recipient and is of real or perceived value in the current or the prospective action or decision of recipient. Furthermore, information is interpreted data created from organized, structured, and processed data in a particular context. A data processing cycle. Data processing is the restructuring or reordering of data by people or machines to increase their usefulness and add values for a particular purpose. Data processing consists of the following basic steps: input, processing, and output. These three steps constitute the data processing cycle. Input A. In this step, the input data is prepared in some convenient form for processing. The form will depend on the processing machine. For example, when electronic computers are used, the input data can be recorded on any one of the several types of storage medium, such as hard disk, CD, flash disk, and so on. Processing A. In this step, the input data is changed to produce data in a more useful form. For example, interest can be calculated on deposit to a bank, or a summary of sales for the month can be calculated from the sales orders. Output A. At this stage, the result of the preceding processing step is collected. The particular form of the output data depends on the use of the data. For example, output data may be payroll for employees. A. Data types and their representation. Data types can be described from diverse perspectives. In computer science and computer programming, for instance, a data type is simply an attribute of data that tells the compiler or interpreter how the programmer intends to use the data. A. Data types from computer programming perspective. Almost all programming languages explicitly include the notion of data type, though different languages may use different terminology. Common data types include integers. Int is used to store whole numbers, mathematically known as integers. Booleans. Bool is used to represent restricted to one of two values, true or false. Characters. Char is used to store a single character. Floating point numbers. Float is used to store real numbers. Alphanumeric string. String used to store a combination of characters and numbers. A data type makes the values that expression, such as a variable or a function, might take. This data type defines the operations that can be done on the data, the meaning of the data, and the way values of that type can be stored. Data types from data analytics perspective. From a data analytics point of view, it is important to understand that there are three common types of data types or structures: structured, semi-structured, and unstructured data types. Figure 2.2 below describes the three types of data and metadata. Structured data. Structured data is data that adheres to a predefined data model and is therefore straightforward to analyze. Structured data conforms to a tabular format with a relationship between the different rows and columns. Common examples of structured data are Excel files or SQL databases. Each of these has structured rows and columns that can be sorted. Semi-structured data. Semi-structured data is a form of structured data that does not conform with the formal structure of data models associated with relational databases or other forms of data tables, but nonetheless, contains tags or other markers to separate semantic elements and enforce hierarchies of records and fields within the data. Therefore, it is also known as a self-describing structure. Examples of semi-structured data include JSON and XML are forms of semi-structured data. Unstructured data. Unstructured data is information that either does not have a predefined data model or is not organized in a predefined manner. Unstructured information is typically text-heavy but may contain data such as dates, numbers, and facts as well. This results in irregularities and ambiguities that make it difficult to understand using traditional programs as compared to data stored in structured databases. Common examples of unstructured data include audio, video files or NoSQL databases. A metadata. A data about data. The last category of data type is metadata. From a technical point of view, this is not a separate data structure, but it is one of the most important elements for big data analysis and big data solutions. Metadata is data about data. It provides additional information about a specific set of data. In a set of photographs, for example, metadata could describe when and where the photos were taken. The metadata then provides fields for dates and locations which, by themselves, can be considered structured data. Because of this reason, metadata is frequently used by big data solutions for initial analysis. Data value chain. The data value chain is introduced to describe the information flow within a big data system as a series of steps needed to generate value and useful insights from data. The big data value chain identifies the following key high-level activities. 1. Data acquisition involves structured and unstructured data, event processing, sensor networks, protocols, real-time data streams and multimodality. 2. Data analysis involves stream mining, semantic analysis, machine learning, information extraction, linked data, data discovery, whole world semantics, ecosystems, community data analysis and cross-sectional data analysis. 3. Data curation involves data quality, trust or provenance, annotation, data validation, human data interaction, top-down or bottom-up, community, crowd, human computation, curation at scale, incentivization, automation and interoperability. 4. Data storage involves in-memory DBs, NoSQL DBs, now SQL DBs, cloud storage, query interfaces, scalability and performance, data models, consistency availability, partition tolerance, security and privacy and standardization. 5. Data usage involves decision support, prediction, in-use analytics, simulation, exploration, visualization, modeling, control and domain-specific usage. 2.4.1 Data acquisition. It is the process of gathering, filtering, and cleaning data before it is put in a data warehouse or any other storage solution on which data analysis can be carried out. Data acquisition is one of the major big data challenges in terms of infrastructure requirements. The infrastructure required to support the acquisition of big data must deliver low, predictable latency in both capturing data and in executing queries, be able to handle very high transaction volumes, often in a distributed environment, and support flexible and dynamic data structures. Data analysis. It is concerned with making the raw data acquired amenable to use in decision making as well as domain-specific usage. Data analysis involves exploring, transforming, and modeling data with the goal of highlighting relevant data, synthesizing and extracting useful hidden information with high potential from a business point of view. Related areas include data mining, business intelligence, and machine learning. Data curation. It is the active management of data over its life cycle to ensure it meets the necessary data quality requirements for its effective usage. Data curation processes can be categorized into different activities such as content creation, selection, classification, transformation, validation, and preservation. Data curation is performed by expert curators that are responsible for improving the accessibility and quality of data. Data curators, also known as scientific curators or data annotators, hold the responsibility of ensuring that data are trustworthy, discoverable, accessible, reusable and fit their purpose. A key trend for the duration of big data utilizes community and crowdsourcing approaches. Data storage. It is the persistence and management of data in a scalable way that satisfies the needs of applications that require fast access to the data. Relational database management systems, RDBMS, have been the main, and almost unique, a solution to the storage paradigm for nearly 40 years. However, the ACID, atomicity, consistency, isolation, and durability, properties that guarantee database transactions, lack flexibility with regard to schema changes and the performance and fault tolerance when data volumes and complexity grow, making them unsuitable for big data scenarios. NoSQL technologies have been designed with the scalability goal in mind and present a wide range of solutions based on alternative data models. Data usage. It covers the data-driven business activities that need access to data, its analysis, and the tools needed to integrate the data analysis within the business activity. Data usage and business decision-making can enhance competitiveness through the reduction of costs, increased added value, or any other parameter that can be measured against existing performance criteria. Basic concepts of big data. Big data is a blanket term for the non-traditional strategies and technologies needed to gather, organize, process, and gather insights from large datasets. While the problem of working with data that exceeds the computing power or storage of a single computer is not new, the pervasiveness, scale, and value of this type of computing have greatly expanded in recent years. In this section, we will talk about big data on a fundamental level and define common concepts you might come across. We will also take a high-level look at some of the processes and technologies currently being used in this space. What is big data? Big data is the term for a collection of data sets so large and complex that it becomes difficult to process using on-hand database management tools or traditional data processing applications. In this context, a large dataset means a dataset too large to reasonably process or store with traditional tooling or on a single computer. This means that the common scale of big datasets is constantly shifting and may vary significantly from organization to organization. Big data is characterized by 3 volts and more: volume, large amounts of data, zettabytes; massive datasets, velocity, data is live streaming or in motion; variety, data comes in many different forms from diverse sources; veracity, can we trust the data? How accurate is it? Etc. Data at rest involves terabytes to exabytes of existing data to process. Data in motion is streaming data, milliseconds to seconds to respond. Data can exist in many forms such as structured, unstructured, text and multimedia. Data in doubt is uncertainty due to data inconsistency and incompleteness, ambiguity, latency, deception and model approximations. A clustered computing and Hadoop ecosystem. Clustered computing. Because of the qualities of big data, individual computers are often inadequate for handling the data at most stages. To better address the high storage and computational needs of big data, computer clusters are a better fit. Big data clustering software combines the resources of many smaller machines, seeking to provide a number of benefits. Resource pooling. Combining the available storage space to hold data is a clear benefit, but CPU and memory pooling are also extremely important. Processing large datasets requires large amounts of all 3 of these resources. High availability. Clusters can provide varying levels of fault tolerance and availability guarantees to prevent hardware or software failures from affecting access to data and processing. This becomes increasingly important as we continue to emphasize the importance of real-time analytics. Easy scalability. Clusters make it easy to scale horizontally by adding additional machines to the group. This means the system can react to changes in resource requirements without expanding the physical resources on a machine. Using clusters requires a solution for managing cluster membership, coordinating resource sharing, and scheduling actual work on individual nodes. Cluster membership and resource allocation can be handled by software like Hadoop's Yarn, which stands for Yet Another Resource Negotiator. The assembled computing cluster often acts as a foundation that other software interfaces with to process the data. The machines involved in the computing cluster are also typically involved with the management of a distributed storage system, which we will talk about when we discuss data persistence. A Hadoop and its ecosystem. Hadoop is an open source framework intended to make interaction with big data easier. It is a framework that allows for the distributed processing of large datasets across clusters of computers using simple programming models. It is inspired by a technical document published by Google. The 4 key characteristics of Hadoop are: economical. Its systems are highly economical as ordinary computers can be used for data processing. Reliable. It is reliable as it stores copies of the data on different machines and is resistant to hardware failure. Scalable. It is easily scalable both horizontally and vertically. A few extra nodes help in scaling up the framework. Since flexible, it is flexible and you can store as much structured and unstructured data as you need to and decide to use them later. Hadoop has an ecosystem that has evolved from its 4 core components: data management, access, processing, and storage. It is continuously growing to meet the needs of big data. It comprises the following components and many others: HDFS, Hadoop Distributed File System, Yarn, yet another resource negotiator, MapReduce, Programming-Based Data Processing, Spark, In-Memory Data Processing, Pig, Hive, Query-Based Processing of Data Services, Base, NoSQL Database, Mahout, SparkMLlib, Machine Learning Algorithm Libraries, Solr, Lucene, Searching and Indexing, Skeeper, Managing Cluster, Oozie, Job Scheduling. Figure 2. 5 depicts a Hadoop system with data storage systems at the bottom with an arrow pointing upwards to data accessing systems. From the data processing systems such as MapReduce and Yarn, another arrow points outward and upward to data access systems and then to data management systems. Big data life cycle with Hadoop. Ingesting data into the system. The first stage of big data processing is ingest. The data is ingested or transferred to Hadoop from various sources such as relational databases, systems, or local files. Scoop transfers data from RDBMS to HDFS, whereas Flume transfers event data. Processing the data in storage. The second stage is processing. In this stage, the data is stored and processed. The data is stored in the distributed file system, HDFS, and the NoSQL distributed data base. Spark and MapReduce perform data processing, computing and analyzing data. The third stage is to analyze. Here, the data is analyzed by processing frameworks such as Pig, Hive, and Impala. Pig converts the data using a MapReduce and then analyzes it. Hive is also based on the MapReduce programming and is most suitable for structured data. Visualizing the results. The fourth stage is access, which is performed by tools such as Hue and Clutter Search. In this stage, the analyzed data can be accessed by users. This is the end of this audio session. We have finished Chapter 1 of Emerging Technologies. You should now be able to develop knowledge about the era of industrial revolutions, identify the technological advances that made the Industrial Revolution possible, analyze the changing conditions created by the Industrial Revolution in both Europe and the United States, and understand the causes of the Industrial Revolution in Great Britain, continental Europe, and the United States. Test yourself more to see that you can describe the technological innovations that spurred industrialization, identifies and understand the programmable device, understand concepts relating to the design of human-computer interfaces in ways making computer-based systems comprehensive, friendly and usable, and develop general knowledge about emerging technologies. Feel free to listen to this audiobook again if you are unsure. Visit our channel for the next section. Thank you for reading with us.